Now we'll concentrate on the second part of the chapter solutions, and here we will be focusing majorly on concentration. How can we measure concentration of different solutions? So concentration essentially tells us how much amount of the solute and solvent have been mixed together. If anything which has higher amount of solute, that means that solution is more concentrated. For instance, you might have heard sometimes, if you have worked in chemistry labs, you might have heard that this acid is concentrated, you need to be careful when working with it. This acid is dilute. So when we are talking about those dilutions and concentrations of solutions, we are talking about the amount of solute that is dissolved in that solution. So concentration basically can be defined as concentration of any solution will be equal to the amount of solute divided by the amount of solution. So the amount of solute that is dissolved in a certain given amount of solution. Now these amounts can be measured in various units. So the amount could be mass, right? Amount of solute can be measured in grams, and similarly amount of solution can be measured in grams. First important thing you need to remember is it's always solute over the solution. Okay, so basically it's solute over solute plus solvent. You would never see solute over solvent. It is solute over solution. Okay, now if it's in mass, it's grams over grams, grams of solute over grams of solution, or kilograms of solute over kilograms of solution. Basically any unit of mass can be used here, and that whenever masses are used together, that is called as mass percent. It can also be abbreviated as m over m. That means the solute has been measured in grams as well as the solution amount has been measured in grams. The next other variation we could do is, instead of measuring grams, let's say I want to measure the volume of the solute and volume of solution mixed in. So for instance, if I say I have ml of solute mixed in a certain ml of solution. Now this form of concentration is called as volume percent, which means it can be abbreviated as volume over volume. So here the mass amount of the solute is also measured in ml, and amount of solution is also measured in ml. And why are we calling these percentages? Basically this is amount of solute over amount of solution times 100. So these are all taken out as percentages. So the actual formula would be concentration. This would be amount, let's say grams of solute over grams of solution times 100. So since all of them are calculated in percentage, it is called mass percent, volume percent. Okay. The other form of unit could be that my solute, let's say I measured it in grams, but my solution was measured in ml. So in this case, this is mass, this is volume. So therefore this particular unit of concentration is usually referred to as mass over volume percent. So it can be abbreviated as m over v. Here, whenever we express something in mass over volume percent, we usually say it is grams of solute in certain ml of solution. Okay. The last unit that you would see is a little different from all these that we saw before. The last unit in amount of solute here, instead of measuring the mass or the volume of that, we measure it in moles. So basically amount of solute here would be measured in moles, and amount of solution would be measured in liters. So this is a very commonly used unit in chemistry, which is referred to as molarity. Okay, molarity is moles of solute divided by liters of solution. So molarity can be abbreviated as capital M. Again, this is capital M, not small m. Small m has a completely different definition. So whenever you see any numbers followed by a capital M, that means we are talking about molarity of that solution, and that is a unit of concentration. So there the amount of solute is measured in moles, and the volume of the solution is measured in liters. The rest of those you saw it in ml, whereas in case of molarity it always has to be in liters. Okay, now let's see each of these concentration units quickly, separate from each other. Okay, so for instance, I have mass percentage, which is mass over mass. This is a percent which is calculated by concentration of mass of the solute and mass of solution. So here we have mass of solute divided by mass of solute plus mass of solvent, or you could add those up and call it mass of solution times 100. That would be the exact formula for mass percentage. So now if the question is asking you to calculate these concentrations, you would always use these formulas that we saw here or we saw in the previous slide. Okay, remember this. This is like a trick to solve questions of for concentration. If the question in the question it is asking you to calculate the mass percentage, or it's asking you to calculate the concentration of a solution, you want to basically write down that formula for that particular concentration and then figure out if you have all the factors that are needed in that formula. For instance, if we want to calculate mass percent, I need to know what is the mass of the solute and what is mass of the solution. Either these would be given to you directly in question, or you need to somehow figure out these particular values and plug those in. But if the mass percent or the concentrations, any unit of concentration is given to you in question, okay, they're not asking you to calculate it. If it is given to you in question, always use it as a conversion factor. Okay, what does that mean? So for instance, if I tell you I have a 10% NaCl solution, 10% mass over mass NaCl solution. Okay, what does that mean? That means I can convert this into a conversion factor where I would have 10 grams of NaCl in 100 grams of solution. Okay, so this is my conversion factor. I could basically, instead of writing this in, I could write this, oh, NaCl equals 100 gram of solution. So this would be my conversion factor to go from grams of NaCl to grams of solution. So if the concentration of a solution is given to you in question, use it as a conversion factor. Okay, let's try make another example of this. For instance, if in a question it's given to me that we have a solution which is, let's write it down here. If the question tells me that we have a 15.0 mass over mass percent KNO3 solution in water, okay, if this is given to me, I would use this as a conversion factor. This information you could plug it into formula and figure that out, that you have 15 grams of solute or this. The easiest way is when you see this, remember this is mass percent. Percent is always calculated out of 100. So if I assume I have 100 grams, this is mass over mass. So I would assume I have 100 grams of solution, which means I can write this as I have 15.0 grams of solute. What is my solute here? KNO3 is going to be equal to 100 grams of this particular solution. Okay, so this would be my conversion factor that I can get from this particular concentration. So again, if the question wants you to calculate a concentration, use this formula. Okay, if you want to figure out what is mass over mass percentage, you need to figure out what is mass of solute, what is mass of solution, and plug it into the formula. If the question gives you a concentration, then use it as a conversion factor. Okay, for instance, when the question tells you right here, when 42.0 grams of water is added to 8 grams of KCl, the mass percent concentration is 16.0 mass over mass. How did we get this number? Let's say the question was when 42 grams of water is added to 8 grams of KCl. What is the mass percent concentration? Let's calculate that. The mass percent in that case, which would be m over m, is going to be mass of solute In this case, we have 42 grams of water, 8 grams of KCl. So which one is solute? The one in lesser amount is our solute. So KCl is my solute here. So grams of KCl divided by grams of solution. Remember this. It's not solvent. It's not solute. It is grams of solution times 100. Do I have grams of KCl? Yes. Do I have grams of solution? I have grams of water. So I don't have grams of solution, but I do have grams of solute and grams of my solvent. So what would be the grams of solution here? Let's write down grams of KCl, which is 8.00 grams. Grams of solution would be solute, which is 8.00 grams, plus the grams of solvent, which is 42.00 grams in total. So when we add the solute and solvent together, that gives us solution times 100. Okay, so this would be your final answer. 8 divided by 8 plus 42 times 100. If you plug this into your calculator, it would give you 16% mass over mass. Okay, and our number of sig figs we are looking for, see here it's also 2 sig figs, and this addition means 2 decimal places. So basically we are looking for 1, 2, 3 sig figs in our final answer. This is 2. So final answer would be 16.0 mass over mass percentage. Okay. Let's take a look at the next question here. Next example. What is the mass percent of sodium hydroxide in a solution prepared by dissolving 30.0 grams of sodium hydroxide in 120 grams of water? Now, first thing you need to identify is which one is solute and which is the solvent. Solute would be here the lesser amount, which is sodium hydroxide, and our solvent is water. Now again the question is asking what is mass percent. Mass percent would be mass over mass, which is solute grams divided by solution grams times 100, right? Do I have grams of solute? Yes. Do I have grams of solution? No, but I do have grams of solvent. So I can find this out by adding the solute and solvent together, right? So what would be my mass over mass here? This will be equal to mass of solute, which is 30.0 grams divided by 30.0 plus 120.0, add these up, times 100. If you plug this into calculator, that would give you 30.0 grams divided by 150.0 grams times 100. So grams and grams got cancelled. Now your final answer is in percentage, which would give you 20.0% NaOH solution. So this is our concentration. Okay. Again, this is when the question is asking you to calculate the mass percent. You use the formula. Okay. The next kind of concentration we saw was volume percent, which is volume of the solute divided by the volume of solution times 100. And again, if the question tells you you have a 10% volume by volume solution of NaOH, you would use this information as a conversion factor. You can use this information to develop this conversion factor, which would be 10 ml. Again, volume over volume, we usually talk it in terms of ml. It's going to be same unit of volume. Okay, if this is ml, this is also ml. If this is liters, assume this is also liters. So this would be 10 ml of NaOH is equal to 100 ml of solution. Always you would assume your solution is of total amount of 100. Okay, why? Because again this is percentage. Percentages maximum are calculated out of 100. Okay, last is mass over volume percentage. So here it is mass of the solute, mass over volume, right? So mass of the solute over volume of solution times 100. So in this case, this is a little tricky. In this case, whenever, or not really, if I say you have 10% mass over volume of a solute of NaOH solution. Then how can we convert this into a conversion factor? It would be 10 grams of NaOH will be equal to 100 ml of the solution. Okay, again, maximum is taken out of 100. Okay, so this is again showing you that you could develop conversion factors based off of values that are given to you. Okay. Okay, the next concentration unit we'll talk about is molarity. This is a little tricky one, and this is the most important one, which is the most commonly used concentration unit in chemistry. It's a little tricky because the name really doesn't give you much information like the others. Here, molarity, you have to memorize that. Molarity basically means moles of the solute over liters of solution. Okay, remember this. Molarity, this is the formula for molarity. This is not a percentage. This is simply moles of solute divided by liters of solution. So this is very important unit that is used very commonly all throughout chemistry, and you will see this being used all throughout this course. So make sure you understand this particular unit. Again, the rule is same like we saw, that if the question is asking you to calculate molarity, you use this particular formula, which means if you want to calculate molarity, you need to figure out moles of solute and liters of solutions. Once you have that, you can basically figure out molarity by plugging in the numbers into this formula. But if, let's say, the concentration is given to you in question, again you would use that as a conversion factor. How? Let's say if I have 10, oops, let's say if we have 10.0 molar NaOH solution, how can we convert this into a conversion factor? 10 molar means, capital M means molar. Okay, so 10 molar means you have 10.0 moles of NaOH in 1 liter of solution. Okay, so basically this is 10. 10 means you have 10 moles over 1, right? That would give you 10. So that is why 10 molar means you have 10 moles of solute in 1 liter of solution. So that is how you can come up with a conversion factor for this particular concentration unit. Okay. Now let's see a question. Don't look at the answer yet. Let's try to solve this question by ourselves. So the question is, what is the molarity of a 0.500 liters of NaOH solution if it contains 6 grams of NaOH? So the question is asking what is molarity, meaning it is asking me to calculate concentration. And what has the question given me? It has given me that we have 6 grams of NaOH, which is our solute, and we have 0.500 liters of solution. So it is giving me grams of solute and liters of solution. What is molarity? Molarity is moles of solute over liters of solution. Okay, how do I solve this? Do I have liters of solution given to me in question? Yes, it's given. Do I have moles of solute given to me in question? No. What's given to me in question is grams of solute. But can I go from grams to moles? Yes. What is the conversion factor to go from grams of NaOH to moles of NaOH? What is the relationship? If you guys have seen the previous chapter videos, you would know the relationship that relates grams and moles is called molar mass. Right? How can we find molar mass? You basically take mass of one sodium atom from periodic table plus the mass of one oxygen atom plus the mass of one hydrogen atom, and that would give you a total mass. When you add it up, the sum would be 40.00 grams of sodium hydroxide. So that is the molar mass of this particular NaOH molecule. Okay, so we can make a relationship here that 1 mole of NaOH is equal to 40.0 grams of NaOH. And using this conversion factor, I can go from grams to moles. So how would I start? I'll start with the grams which is given to me, which is 6.00 grams of NaOH. To convert these grams into moles, I'm going to divide these grams, cancel these grams. I'm going to divide by grams, multiply by moles. And how many moles? 1 mole. How many grams? 40 grams. So you plug in the values, grams and grams got cancelled. Your final answer is in moles of NaOH, which will come out to be 0.150 moles. Now we have moles of solute, and we already had liters of solute, so you plug in the values right here. How many moles? Moles were given right here. We just calculated 0.150 moles divided by liters. How many liters? 0.500 liters. So you plug those values in right here, and your final answer would be, you put these values into calculator, and moles over liter, again you can't cancel it, right? But moles over liter can be written as capital M, which would, if you plug this into calculator, it would give you 0.300 molar. So that would be our final answer. Now, in case instead, if the question didn't give you liters of solution, and let's say it gave you milliliters of solution, remember for formula we need liters. So you would have to convert ml to liters. Okay, so basically the idea is the question could give you any form of the amount of solute or any form in the any unit for volume of solution. You have to somehow come up with these particular units, which is moles of solute and liters of solution, and plug them in here, and that would give you your final answer. Okay, for let's try another question. For instance, right here, the question is saying what is the molarity of 0.225 liters of KNO3 solution, potassium nitrate solution, containing 34.8 grams of potassium nitrate. Molar mass, mm is molar mass of potassium nitrate is given to you. It is 101.11 grams per mole. So the question is, what is molarity? So I need to solve for molarity. What is the formula that we know for molarity? We know it's moles of solute divided by liters of solution. Do we have moles of solute given to us? No. Do I have liters of solution given to me? Yes, that's right here. But instead of moles, is there any other information that's given to me? I have been given grams of solute. So again, I can go from grams to moles. How? Using molar mass. Grams of KNO3 are given to me. I need to somehow figure out moles of KNO3. Oops. And the conversion factor here is going to be again molar mass. So I know that 1 mole of KNO3 will be equal to these many grams, which is 101.11 grams of KNO3. So that is my conversion factor. We start with what's given, which is 34.8 grams of KNO3. I want to cancel grams, so I'll divide by grams of KNO3, multiply by moles of KNO3. How many moles? 1. How many grams? 101.11 grams, and grams got cancelled. Our final answer is in moles of KNO3. Now if you plug these values into your calculator, that would give you 0.344 moles of KNO3, potassium nitrate. Now we have moles. So now we have moles and liters. We simply plug these values into our formula. So molarity would be 0.344 moles of potassium nitrate over liters of solution, which was given to us 0.225 liters. Remember, this has to be in liters, it cannot be in ml. So now if you plug this into your calculator, that would give you 1.52968. That's what I have, these many molar. But how many sig figs are we looking for? This is capital M. How many sig figs are we looking for? 1, 2, 3. That means right here. So my final answer would be 1.53 molar. So that is the final concentration of this particular solution. Okay. All right. So again, this is giving you example of conversion factors, but we have already seen those. So now let's try a question like this. So the question says, how many grams of NaOH are needed to prepare a 75 gram of 14% mass over mass NaOH solution? So let's first figure out what exactly is given to us in question and what is it asking. It is telling us we have a solution of sodium hydroxide which is 14% mass over mass. So this is 14% mass over mass over mass solution. This is given to us in question, and what's given is how many grams. So question is asking how many grams of NaOH is needed to prepare 75 grams of this solution. So what's given to us is mass of solution, right? Because the unit that you see is 75.0 grams. So if the unit is grams, you know it's talking about mass. So mass of solution is given and the question is asking what is the mass, meaning grams of NaOH. What is NaOH here? It is our solute. So question is asking how many grams of solute. Okay. Now remember when I said whenever concentration is given to you in question, use it as a conversion factor. So how can I use this information? I will rewrite this information as this is mass over mass, meaning it is 14 grams of solute, which is NaOH, equal to 100 grams of solution. Okay, mass over mass, remember, is grams of solute over grams of solution, right, times 100. So in this case, if it is 14%, it means this is 14 grams and this is 100 grams. That's what I wrote here. Now the question is asking me to go from grams of solution to grams of solute. Do we have a conversion factor that relates grams of solution and grams of solute? Right here, grams of solution, grams of solute. So we can use this conversion factor to go from solution to solute. We start with what's given, which is 75.0 grams of solution. I want to cancel the grams of solution, which is right here. So I divide by grams of solution and multiply by the other side, which is grams of solute, or which is NaOH in our case. How many grams of solution? 100. How many grams of solute or NaOH? 14. So this grams and this grams got cancelled. Your final unit that you see here is grams of NaOH. So by unit, it's working. Right, now let's plug in the values into calculator. That would be 75 times 14 divided by 100. That is giving me final answer of 10.5 grams of NaOH. Okay, how many sig figs are we looking? Remember, this is, I wrote it as 14, it's actually 14.0. So this is 3 sig figs. This is also 3 sig figs. So my answer should have 3 sig figs, which is 1, 2, 3, correct. So my final answer is 10.5 grams of NaOH in 75 grams of solution would give us 14% solution of NaOH. Okay, so remember, whenever the question gives you this information, use it as a conversion factor. Okay, let's try one more question of this similar concept. So question is asking how many grams of AlCl3 are needed to prepare a 125 ml of 0.150 molar solution. Okay, now again, first figure out what's given to you in question and what is it asking. Question is asking how many grams of AlCl3. Okay, so I have to figure out grams of AlCl3. That's my question. Are needed to prepare 125 ml of a 0.150 molar solution. So my solution is 0.150 molar. And how much of that solution am I preparing? 125 ml of solution. Okay, so the volume of solution is given to me and molarity of solution is given to me. Question is asking me to figure out grams of AlCl3, which means AlCl3 here is my solute. Okay, since we are talking about a solution of AlCl3. Remember, in most of these solutions, your solvent is water and the solute that is being dissolved is the chemical compound that you see. Okay, now the question is, how can I relate this? What do I do? Only thing, remember, you know about molarity, it is moles over liters. And when molarity is given to you, you use it as a conversion factor. So what is molarity? Remember, molarity is moles of solute over liters of solution, right? Moles of solute. So let's convert this into our conversion factor. If molarity is 0.150, that means I can rewrite this as 0.150 moles of solute, which is AlCl3, is equal to 1 liter of solution. So now I can go from, if I know the volume of solution liters, I can relate it to moles. Do I have liters of solution given to me? No, but I do have ml of solution given to me. So if I convert this ml into liters, I can go from liters to moles, and then question is asking me for grams. I know there is a relationship that can take me from moles to grams. Okay, so that kind of gives you an idea of what is the sequence for the solution. Okay, but don't do this in one single step. First, try to make your solution map. So again, let me repeat that. We will rewrite our concentration in terms of a conversion factor, and we are going to find a common factor that relates any of these units that you see in conversion factor. I have moles and I have liters. The liters that you see, liters of solution, is also given to me right here in ml. The question is giving me ml of solution, so my first step would be I will convert this ml into liters of solution. Then I can go from liters of solution to moles of AlCl3 using this conversion factor, right? So this is my conversion factor. Then I can go from moles of AlCl3 to grams of AlCl3 using the molar mass. For that, let's figure out what is the molar mass of AlCl3. So if you look up your periodic table, the mass of each of the atom, Al is given as 26.98 grams of Al. We have one of those, and then we have 3 of chlorides. So it would be 3 times each chloride is 35.45. Oops, 45 grams of Cl. You add all of this together, both of these together, and that would give you a mass of 133.33 grams. Okay, so that means my conversion factor for here is going to be 1 mole of AlCl3 equals 133.33 grams of AlCl3. Okay, so that is my conversion factor. And last step was this. What is the conversion factor here? We know that 1 liter equals 1000 ml. So that is my conversion factor to use for this step. Okay, so now we have our solution map completely figured out with each conversion factor. Now we can start solving. Okay, I'm going to just separate this out for now. Let's start with what's given, which is 125 ml. So 125 ml, I want to cancel the ml, convert to liters. So that would be liters. Oh, I want to cancel the ml, so I divide by ml, multiply by liters of solution. I'll abbreviate it like this, SOL. 1000 ml, 1 liter. ml got cancelled. My answer is in liters of solution. So I'm right here. Now I go from liters to moles. So to cancel liters, I divide by liters of solution, multiply by moles of AlCl3. How many liters? Right here, the conversion factor, moles is 0.150 moles, liter is 1. Liter got cancelled, our final answer is in moles. Now I'm right here, so I need to go from moles to grams. So to cancel the moles, I divide by moles and multiply by the other side of conversion factor, which is grams of AlCl3. How many mole? 1 mole. How many grams? 133.33 grams. Moles and moles got cancelled. My final answer unit you can see is grams of AlCl3. Now if you simply plug all the numbers into calculator, that would be 125 times 0.150 times 133.33 divided by 1000. That is giving me grams of 2.4999 grams of AlCl3. How many sig figs are we looking for? The question gave me only two values, which is this has 3 sig figs, this has 3 sig figs. So my final answer should have 1, 2, 3 sig figs. That would be 2.50 grams of AlCl3. So our final answer is 2.50 grams. Okay, so always use this as a conversion factor and then see what is the information that is given to you. Okay, if this is my conversion factor, only information that is given to me is 125. So your starting point will always be 125 ml. Now you have to figure out a relationship to go from ml to grams. So the only conversion factor you see here is this. This is ml is volume, liters is also volume, which means you need to go from ml to liters first. Then you can go from liters to moles, and then moles to grams is using molar mass. Okay, so that way you can form your solution map. Right? Okay. Next concept is dilution. So a very common process that is used in chemistry is that a concentrated solution is prepared at once, which is called the stock solution, and then different concentration, dilute concentrations of solution can be prepared using that stock concentration. So dilution is a process where for instance, right here, if we have this particular solution right now in here, and let's say the concentration of this solution is 10 molar, but I am looking for something lesser concentration, we can take some of the concentrated solution here and add some more solvent or water into this, such that what would happen, the amount of solute will stay the same, but the total amount of solution will increase because we are adding more solvent. So the solution will here become more diluted. So basically, if you take 1 cup, if you take a big jug of filled up with water, and let's say I added 5 grams of sugar or 5 spoons of sugar into this, and I filled it up with 50 ml of water. Okay, and rest, let's say, is 50 ml of water. We mixed it, we dissolved it. I was trying to make this solution for lemonade, and I tasted it and I was like, oh no, I added too much sugar, it tastes too sweet. What do we usually do? We basically add some more water into it to cut down some of the sweetness. What are we doing here? Basically, we are now, let me separate this, we are now basically diluting this solution. We are diluting the amount of sugar that is present in this particular solution. So it still has 5 grams of sugar. Only thing now is that because I added another 50 ml of water, let's make it different color. This is like a second time I added another 50 ml of water. So now I have 5 grams of sugar in a total of 100 ml of water. So initially the concentration was 5 grams in 50 ml, and now my concentration is 5 grams in 100 ml, right? So what happened here is basically the concentration got diluted. The concentration for this sample was 0.1 gram per ml, and concentration for this solution is 0.05 gram per ml. So basically you can see right here the concentration is reduced, and this process is called the process of dilution, and this solution which is less concentrated is called the diluted solution. A less concentrated solution is diluted solution. So only thing that is changing here is the volume of the solution is increasing and the concentration is decreasing. The total amount of solute stays the same. Okay, so usually whenever you see a solution is being diluted, or a solution is, we are changing the concentration of a solution, and only thing we are changing is the amount of solvent, and the amount of solute stays the same, we can use a very simple formula there, which is called C1V1 is equal to C2V2. Here 1 is the initial solution, so concentration, C stands here for concentration, V stands here for volume. So concentration of solution 1 times the volume of solution 1 is going to be equal to concentration of the solution 2 times the volume of solution 2. You could regard here the solution 1 as your initial solution and solution 2 as your final solution. How did we end up with this? Basically, if you remember, molarity is moles of solute over volume of solution. So if I rearrange this equation, I can say that moles of solute is equal to molarity times the volume of solution, right? And I know that when I dilute the two solutions like we saw previously, we are not changing the moles of solution. So moles of solute 1 and moles of solute 2 are going to be equal. Moles of solute 1 would be molarity of 1 times the volume of 1. Moles of solute 2 are going to be molarity of 2, volume of 2. And we know that moles of 1 equals moles of 2. So you can simply write M1V1 equals M2V2. Right? And that's exactly what this equation is. When you write specifically capital M, we are here talking about molarity. But concentration can have multiple units, so this here can have any unit. This can be any unit of concentration. It can be mass percent by mass over mass, volume over volume percent, or mass over volume percent, or it can be molarity. So you might see it used interchangeably. People like to use M1V1 equals M2V2 or C1V1 equals C2V2, depending on what concentrations you're working with. Okay, what is important here? You should remember that the units of C1 and C2 have to be same, and the units of V1 and V2 have to be same. For instance, if V1 is in ml, your V2 has to be in ml. If your V1 is in liters, V2 has to be in liters. Okay, let's try a question. For instance, the question is, what is the final concentration when 0.5 liters of 6 molar HCl solution is diluted to a final volume of 1 liter? So question is asking what is final concentration. Final is C2. When 0.5 liters of 6 molar HCl solution is diluted to a final volume of 1 liter. So this volume is final volume, which is V2. And these are our initial conditions where 0.5 liter is volume. So this is initial volume V1. And this is 6 molar. Molar means concentration. So this is C1. Now what is the expression we know? It is C1 V1 equals C2 V2. What am I solving for? I'm solving for C2 here. So C2 right here. If I'm solving for this, means I need to get rid of this V2 from here. So if I want to get rid of V2, here V2 is in multiplication. So I divide by V2. That cancels this V2 out. I cannot simply divide one side. I have to divide on the other side of the equal sign as well. So I divide on this side as well, which means C2 is C1 V1 over V2. Now you simply plug in the values here. What was C1? C1 is 6 molar times V1, which is 0.50 liters, divided by V2, which is 1.0 liters. Oh, liters. So make sure these units are same. So see, liters and liters can cancel out. But if it was different unit, you would not be able to cancel it. Okay. So here we cancel them out. Our final answer is in molarity, which is our C2. So C2 here is going to be 6 times 0.5 divided by 1, which will give you 3.0 molar of HCl. Okay, what's important here, make sure you do not make an error when assigning what is initial concentration, initial volume, and final concentration and final volume, because that is majorly the issue where people make mistakes. The other error that sometimes students make is the units. They don't pay attention that the units are same or different. Okay, moving on, next question. Let's try this. What volume of a 2% HCl solution can be prepared by diluting 25 ml of 14% HCl solution? So what volume of 2% solution? Now again, this is based on all English. Okay, this is not chemistry. Here you have to first pay attention on the English. What volume of 2% HCl solution can be prepared by diluting 25 ml of 14 molar. So what are we diluting? We are diluting this solution, and this is the volume and this is the concentration of one of the solutions. Okay, so this would be my V1 and this would be my C1. Okay, you could assign it V2 or C2, it really doesn't matter, as long as this is your solution number 1 or solution number 2. So this should be same solution. Okay, what volume? Question is asking what is my final volume that can be prepared of this particular concentration, C2, which is 2%. Okay, so I have C2, C1, and V1. Question is asking what is V2. Now remember the units. C1 and C2 are both mass over volume, which is good. They are same. Now you simply do C1 V1 equals C2 V2. I am solving for V2, which means I will divide both the sides by, I need to get rid of this C2 from here, so I divided by C2, cancelled. I can just divide one side, I divide the other side by C2 as well. So my V2 here is C1 V1 over C2. That you see right here, C1 V1. Oh, this should be C1 V1 over C2. Now you simply plug in the values. V1 was 25 times C1 was 14 divided by 2. Percent mole over volume, percent mass over volume will get cancelled. We are left with 25 times 14 over 2, which would give you 175 ml. Again, number of sig figs 3, 3, 3. So final answer is 3. Right. One more practice question. So for instance, right here, what is the mass over volume percent of a solution prepared by diluting 10 ml of 9% NaOH to 60 ml. So what are we diluting? We are diluting 10 ml of a solution which is 9%. So this is my V1, this is C1. I'm diluting it to 60 ml, so this is my final volume, so this is V2. And what is the percent of solution prepared means this is the final solution being prepared, so this is C2. Again, what am I solving for? C2. So what's the formula? C1 V1 equals C2 V2. I'm solving for this, so I need to get rid of V2, so I divide by V2 on both the sides. This and this got cancelled. My answer is that C2 equals, no, let's rewrite it here, C2 equals C1 V1 over V2. C1 was right here 9%, 9.00%, times V1, which is 10.0 ml, divided by V2, which is 60.0 ml. Again, see ml is same, so I can cancel it out. If one of these was liters, we would first convert that into ml. And now the final answer is 9 times 10 divided by 60, which would give you 1.50%. And 9 was mass over volume, so this would also be mass over volume. Everything's 3 sig figs. here. So answer is 3 sig figs. Let's try one more quick question. Another example, what is the molarity of a solution prepared by diluting 0.180 liters of 0.6 molar HNO3 to 0.540 liters? So again, what is the question asking? What is the molarity of solution prepared? So this is final concentration by diluting these many liters. So this is initial volume of initial concentration to this much. So this is the final volume. And the formula again is M1 V1 equals M2 V2. I'm only using M here because the question says molarity. You would simply use C. It really doesn't matter. I'm solving for M2, so I need to get rid of V2. So I divide by V2 on both these sides. That would give me M2 is M1 V1 over V2. Plugging in the values here, M1 is 0.600 molar, V1 is right here 0.180 liters divided by 0.540 liters, which is V2. Again, liters and liters got cancelled. If you plug this into calculator, that is 0.600 times 0.180 divided by 0.54 would give you 0.200 molar. I'm looking for 3 sig figs, 3 sig figs, 3 sig figs. So final answer should have 3 sig figs. So that is my final answer. Okay, next we'll talk about what are different types of mixtures and what are the properties of some of the solutions. So different types of mixture could be solutions, colloid, or suspensions. There are 3 different types we are going to discuss today. So solutions, like we have discussed before, it consists of a solute, which is really small particles, ions, or molecules that have been dissolved into a solvent. It's a very uniformly distributed mixture. Uniform distribution of solute and solvent particles, and usually these solutions are transparent. We cannot separate the solute from the solvent. We cannot filter it out. We cannot simply just take example of salt in water. Salt, after it dissolves in water, you cannot simply filter it out. Similarly, they cannot be separated by passing them through a semi-permeable membrane. So a semi-permeable membrane is simply a membrane that is permeable to few things. That's why it's called semi-permeable. And permeable essentially means that it would allow few of the molecules to pass through it. So a semi-permeable means that it would allow some of the chemicals or substances or some of the molecules to pass through the membrane. So if you have like a jar separated by a semi-permeable membrane, that would allow few, and you have 2 different solutions on the 2 sides of the membrane, it would allow few solutions to cross across that membrane. That is a semi-permeable membrane. So solutions cannot be separated into solute and solvents by either filtering or semi-permeable membrane. It just doesn't work. Colloid, on the other hand, is a mixture prepared by adding the particles basically here, or the solute particles that are added. They are a little bit bigger in size than in solution. So these particles are also, they're very similar to solutions in the sense that they also make uniform distribution. They also have uniform distribution or homogeneous distribution. But these cannot be filtered either, but they can be separated by a semi-permeable membrane. So they are large enough that they are separated by a membrane. If there is a semi-permeable membrane which would allow few things to pass through, the colloids can essentially be separated from solute to solvent. An example of colloid would be, for instance, when we talk about fog or dust in air, right? Fog essentially is created by when we have some dust particles in air or clouds. Those are basically example of colloids. They are not very transparent. They have some opacity to them. So that is called, that is an example of colloid. Next type of mixture is called a suspension. A suspension is essentially, for instance, if you mix sand, if you mix like sand or mud in water, that is an example of a suspension. It is a mixture which is non-uniform, meaning it's heterogeneous. So these suspensions, they have very large particles mixed into solvent. But at the end, if we, let's say if we stir the solution and you let it settle down, at some point the solute is going to completely settle down because of its weight, and therefore they can be filtered out from the solution, so they can be separated from each other, and that is the example of a suspension. So for instance, like this, a solution would be something that you're seeing right here. It's very uniformly distributed. A colloid is something that is here shown in yellow, and suspension is something that is settling down at the bottom. So if you are trying to filter the stuff out, by filtration, the suspension will be separated out. If you filter a solution consisting of all three, a mixture consisting of all three types of mixtures, the suspension will be separated out by filtration. And then if you use a semi-permeable membrane, that would separate a colloid from the solution, whereas a solution is something that cannot be separated, okay, through any of these means. Now let's talk about some colligative properties. So a colligative property is basically called a physical property that depends on the concentration of the solution. So the properties by definition are right here. So by definition, colligative properties are the properties, these are essentially physical properties that depend on the concentration of the solute particles that are present in solution, meaning they depend on concentration of the solution. Some of the examples of those are vapor pressure, boiling point, freezing point. For instance, boiling point and vapor pressure. What is vapor pressure? If you guys remember, we have talked about this previously. Vapor pressure is essentially if I have a jar filled up with a liquid in here and I close this lid with a lid, what would happen? Some of this liquid in here, which is on the surface, the molecules that are present on the surface are going to vaporize and build some pressure onto the solution, and this is called vapor pressure, right? But now if you have a solute, so this was assuming this is pure solvent and it has this much vapor pressure. Now when you have a solute, what does a solute consist of? A solution. A solution would have few solvent molecules, right? And it would also alongside have a few molecules of solute on the surface, right? So now the number of molecules of solute and the solvent on the surface are different than the number of molecules of solvent present in a pure solution, in a pure solvent. So here, let me repeat this. Basically, this is a pure solvent. There is no solute mixed here. At the surface, you see all the molecules that are present are molecules of the solvent. But when you have a mixture, you have some molecules of solute and some molecules of solvent. So the probability of now having the number of molecules that will be present as a vapor on top of this is going to be less, because there are fewer molecules that are present on the surface, so fewer of them are going to vaporize, which means whenever you have some solute mixed into a solution, into a solvent, the vapor pressure now is a little bit less. The vapor pressure reduces, whereas in case of pure, there would be a lot more molecules of the solvent that have converted into vapor, so vapor pressure is going to be higher. So as vapor pressure above the solution decreases when a solute is added to water. Whenever a solute is added to water, vapor pressure would decrease. Same is true for similar effect is seen in case of boiling point. The boiling point essentially increases because of the same reason. When do things boil? Whenever the vapor pressure becomes equal to atmospheric pressure. So you could think that it would take it a little longer for the vapor pressure here to become equal to atmospheric pressure, and therefore it would have to boil at a much higher temperature, and therefore the boiling point increases. Now freezing point on the other hand decreases whenever a solute is added. For instance, you could think of whenever ice cream is made, if you have went to those schools where sometimes they are showing like those science fairs and stuff, where they basically make ice cream by putting or milk and sugar into uh, ice with salt, and that salted ice basically freezes the milk very faster, much faster. Then you would freeze it somewhere else, freeze it at normal ice. In normal ice, you would never be able to freeze um, milk, right? But when you add salt into ice, that freezes instantly or very fast. Why is that? Because the freezing point of the solution decreases. When you have a mixture of, let's say, some of the molecules are solute, some of the molecules are solvent, what would happen? What happens in order for it to freeze? In order to freeze, all these molecules of solvent have to come together and form a compact structure, right? They have to freeze, meaning they are turning into solid. So they have to arrange themselves into a crystal structure. Whereas when solute is present, it becomes a little more tricky, because now the crystal is being affected by presence of these solute molecules. Now they are disturbing this crystal structure. So therefore, freezing point in this case, it takes a little longer for the liquid to turn into solid, and that's why freezing point decreases even more. So it needs to release even more heat to freeze, and that is why ice cream can be frozen when you add salt into water. So all these are examples of colligative properties. Vapor pressure decreases, boiling point increases, and freezing point also decreases if the solute is added. More solute means more larger would be the change in vapor pressure, boiling point, or freezing point. Okay. Next, we'll talk about another process which is very crucial in maintaining all the biological functions, all our cells, maintaining the health of all of the cells that are present in our body. And this is also again dependent on concentration of solutions. This process or property is called as osmosis. Osmosis essentially is a process where water or the solvent molecules flow from the lower concentration solution to a higher concentration solution when the two solutions are separated by a semi-permeable membrane. So again, if you have this particular beaker, let's say, and we put a semi-permeable membrane which is able to separate the two solutions from mixing, and on one side I have pure water, on the other side I have water with some sucrose in it, meaning it has some solute. Irrespective of what solute, it just has some solute in it. So this is a pure solvent, this is a mixture on the right side. So now what is the difference here? There is a difference in concentration of solute. This has very low concentration of solute, this has high concentration of solute. So now in this case, in order to make the amount of water on both the sides same, in order to make the concentration on both the sides same, of the amount of water to make it same, water molecules are going to basically move from the low concentration, they're going to flow from the low concentration solution to a higher concentration solution. So eventually, over time, it's a slow process, but over time, what is going to happen, we'll see that some of the water from here, from the left side, is going to enter into the right side of this particular beaker section. And water molecule, as you can see here, the level of water has risen after some time. So basically, where did my cursor go? Water flows into the solution with a higher solute concentration until the flow of water becomes equal in both the directions. Okay, so until the concentration of the two solution kind of become equal with time, it is going to keep on happening. Okay, and what controls when does this stop? This is stopped when osmotic pressure. This is stopped by osmotic pressure, which is equal to the pressure that would prevent the flow of additional water into the more concentrated solution. Okay, so at some point this pressure that is being building up right here because of this difference is going to hold more water from entering in, and this is called the osmotic pressure. Okay, the greater is the number of particles that are present, that are dissolved, the higher is the osmotic pressure. So the solution here, basically the solution which has the solute, is going to have a higher osmotic pressure. Sucrose solution has a higher osmotic pressure than the pure water, which essentially here has an osmotic pressure of 0. Okay, so in this case it will keep on flowing, and eventually the height of the sucrose solution would increase, which is going to create sufficient pressure such that it is going to create sufficient pressure here such that no more water molecules are going to pass through it, and this new pressure that is built on this side is called as the osmotic pressure, which basically now stops the further exchange of water. Okay, why is so important in the biological processes? So basically our cells are present in surrounded by body fluids, right? The cells in our body are surrounded by a bunch of solutions or fluids. For instance, there is blood, there is lymph, there is plasma, there is tissue, different kinds of tissue fluids. All of those solutions are a mixture. They are solutions. That's why we are calling them solutions. They consist of some solute or some sugar mixed into them. And same is true for our cells. Our cells, inside the cells, the environment basically is again water, which consists of certain amount of salt, certain amount of sugar. So it is very important that the amount of sugar and salt which is present outside or inside is maintained at a certain amount, at a certain level. Okay, so that's why whenever some drugs are injected into humans at, let's say, hospitals, they're usually injected in IV solutions. Why is that? You can't simply just take water and inject water into human body. You are injecting IV solutions in there. These IV solution basically mimic the osmotic pressure of our body fluids. Okay, meaning they mimic the concentration of the salt and the concentration of sugar that is present in our body fluid. For instance, our blood glucose is usually 5% mass over volume, and the NaCl or salt concentration is 0.9% mass over volume. This solution is called as an isotonic solution. Iso means same, tonic means tonicity, which is the concentration. So they have the similar concentration in terms of sugar and salt to our blood or our body fluids, and that is called as isotonic solution. Okay, so they basically exert the same osmotic pressure, meaning the solution that you inject is not going to basically come here and make things go in and out of the cell very fast, because there's difference in osmotic pressure, right? Because that's not what we want. We want whatever stays in the cell should stay inside the cell, and whatever is outside the cell should stay outside the cell, right? The exchange of water molecules in and out is going to cause a big issue. For instance, like this. Before we start explaining this, let's try to go over some terminology. So what you saw right now was isotonic solution, which is a solution which has same osmolarity as or same osmotic pressure or same concentration of solutes as our body fluids, right? Hypotonic solution is a solution with a lower osmolarity than the blood plasma, meaning it has less amount of um, solutes. Osmolarity here is basically referring uh, to the osmotic pressure. So less osmotic pressure meaning less concentrated solution, meaning less osmolarity. Okay, so those solutions which have lesser amount are called hypotonic, whereas a solution with higher osmolarity than the blood cells are called hypertonic solution. So now what would happen if they are an isotonic solution? Water, the meaning the osmotic pressure outside and inside the cell is same, so there is not going to be an extra exchange of water in and out of the cell. Whereas now if you take this same cell and we put it into a hypotonic solution, hypo means the osmolarity is lower on the outside. So outside solution is less concentrated, right? Meaning it is hypotonic. Hypo means it's lesser, it's less concentrated, it is a dilute solution. So now you know that water always flows from less concentrated to high concentrated. So if outside is less, water is going to flow from outside to inside, and the blood cells are basically going to swell up to a point that at some point they are going to burst open, and that is called as hemolysis, meaning breaking of the blood cells. Lysis mean break, hemo means coming from hemoglobin, which is RBCs, red blood cells. Okay. Next would be if we take the same cell right here and put it into a hypertonic solution. A hypertonic solution is going to be something which is concentrated, has higher osmolarity, so more solute. So now in this case, what is going to happen? The solution inside the cells is less concentrated, outside the cells is more concentrated. So water is going to flow from low concentration to high, meaning from inside to outside. So this is going to cause the cells to shrink. And this process is called shriveling of the blood cells, or it's called crenation of the blood cells. And that again is not good for us, right? So the cells are basically going to shrink, and therefore it's very important to maintain the body fluids at the same concentration or same tonicity as our blood cells. So everything is usually injected into human body in isotonic solution to maintain the osmolarity around the blood cells. The questions, for instance, can be like this: indicate if each of the following solution is isotonic, hypotonic, or hypertonic. So 2% NaCl solution, remember the NaCl solution was around 0.9 osmolarity. So 0.9%, so NaCl is 0.9%, which means this is way higher. If it is higher, it is hypertonic. So in this case, it is C. Higher, hyper means something higher, right? So 1% glucose, the level of glucose in our blood was 5%, or based on the body fluids was 5%. So this is much lower than that. So this would be hypotonic. 0.5% NaCl is again a little lower than 0.9, which is what we want. So this is going to be lower, meaning hypo. 5% glucose is exactly same of what is found in our blood fluid. So this is going to be an isotonic solution. If it is same as what is wanted, then it is isotonic. Okay. So for instance, when placed in each of the following solution, indicate if the red blood cell will not change: hemolysis, crenation. Crenation is again when it shrinks, and hemolysis is when it swells up. Remember that. Okay, so when you place it in 5% glucose, 5% glucose is again isotonic to our body fluid, so it is going to be no change. 1% glucose means it is lower than what our body has. So outside is less concentrated, inside the cell is high or more concentrated, and liquid always flows from less to high. So inside the cells, it's going to collect a lot more water, so it's going to swell, which means answer is B. 0.5% NaCl solution again is lesser. Usually outside our body is 0.9%. Inside, sorry, it's 0.9 inside the cell, so it is saying we have 0.5, sorry. So if it is 0.5, it means it's less. Inside is again high, so water is going to flow from outside to inside, so again the cells are going to swell up. 2% NaCl solution is a lot high. So inside the cell, remember, is 0.9%, outside is 2%. Now outside is higher, inside is less, so water is going to flow from inside to outside. So our cells are basically going to shrink. They are going to lose water, so answer would be C. Right. And this is like the last kind of question. In each case, tell which side if either rises and why the solvent in water. So you guys can try this. For instance, example is A is 1% glucose, B is 5% glucose. So liquid is going to go from less concentrated to high concentrated. So it's going to rise on the B side, right? So here it's going to rise on B. In part B, basically you have glucose on 0.1, this is 0.5. Again, it's going to go from less to high, so it's going to rise on B side. Again, remember the water always goes from less concentrated to high concentrated. Okay. Another example could be this. For instance, we have 3 molar Na, sorry, 3% NaCl, 3% NaI. It doesn't matter what salt. This will also produce 2 ions. This will also produce 2 ions. It's 3% on both sides, meaning water level is not going to change, not change. Okay. And same thing here, 1 molar, 1 molar. It's NaCl, NaBr, really doesn't matter. So it's going to stay same. Okay. Let's talk about quickly one more process which is done, which you guys might have heard of before, which is dialysis. So where is dialysis used? Basically, it's a process which is very similar to osmosis. In case of dialysis also, what happens, there is a semi-permeable membrane which is called a dialyzing membrane. It allows or permits some small solute molecules and ions and some solvent molecules to pass through, but it basically retains the large particles such as colloids. So it would allow most of the small solute and solvent molecules to pass through, but larger particles it would not allow to pass. And this is a process which is used usually when the kidneys of a person stop functioning well. So the idea is that this dialysing membrane is basically, this is more like a, you can think if it's a cellophane membrane is an example of a dialysing membrane. If you fill it up with like bunch of like bad blood, which is filled up with urea molecules, bunch of the waste products that are created in our body, and we allow this and pass this blood through these dialysis membrane, which is surrounded by a solution which is much more cleaner, which is less concentrated. What would happen? Most of these compounds, which are like bad compounds, the smaller compounds, are going to come out of that blood. So it's going to be lost, right? And the blood that is going to be pumped back into the body is going to be removed from these waste products, right? So basically excess water and the waste products are going to be removed from the bad blood, and that is the whole process of dialysis. So this is also basically based upon osmosis. Only difference is in osmosis only solvent molecules can pass through, whereas in case of dialysis small solute molecules as well as solvent molecules are allowed to pass. So eventually the blood, the concentration of most of the compounds in the blood, which is like let's say salt or sugar, is going to become equal on both the sides, whereas the products which is like urea and other waste products are going to be lost outside into the outside solution, right? So those are some of the processes that are affected by the concentration of the solution. So that wraps up most of the topics for this particular chapter, which is solution. So from here we learned what exactly is a solution, what are different types of these solutions, what are different concentrations of these solutions, and what are different properties of these solutions, right?